Question 3. The vapor leaving the top of a distillation column goes to a condenser in which either total or partial condensation takes place. If a total condenser is used, a portion of the condensate is returned to the top of the column as reflux and the remaining liquid is taken off as the overhead product. Now, if a partial condenser is used instead, the liquid condensate is returned as reflux and the uncondensed vapor is taken off as the overhead product. The overhead product from an N-butane and pentane distillation column is 96 mol% of butane. The temperature of the cooling fluid limits the partial condenser temperature to 40 degrees Celsius or higher. Now for A, using Raoult's law, estimate the minimum pressure at which the condenser can operate as a partial condenser, okay, that is, at which it can produce liquid for reflux, and the minimum pressure at which it can operate as a total condenser. In terms of dew point and bubble point, what do each of these pressures represent for the given temperature? Now, so this is your schematic diagram or a sketch of your process in the condenser unit. So in the case of a partial condenser, we take the dew point of this mixture here to be 40 degrees Celsius. So of this vapor mixture, yeah. So the dew point is actually the temperature at which vapor starts to condensate and becomes liquid phase. Now, given that Raoult's law, so this is your Raoult's law equation, okay, X is the sum of the mole fraction of species in liquid phase, and Y is the mole fraction of the species in vapor phase. P is the total pressure, and Pi star over here is your vapor pressure of your species at that specific dew point temperature. So, since at dew point, the summation of the mole fraction of species in the liquid phase should equals to 1. Therefore, we get that 1 is equal to the sum of the mole fraction of the species in liquid phase, which also equals this. And we rearrange the equation and take the P, okay, the total pressure here out, to solve for this equation over here. Now, we have two species here, which is butane and pentane, so we need to add up both of them. So the mole fraction of butane is 0.96 and the remaining 0.04 is for pentane. And we can solve for their partial pressure for each of the species at 40 degrees Celsius using the Antoine equation, as discussed in previous week's tutorial. Then we substitute the partial pressure along with their mole fraction in vapor phase back into this equation, which is, so this one is your butane and this one is your pentane, which gives you a minimum pressure of 2595 mmHg for your partial condenser. Now, in the case of a total condenser, we take the bubble point of this liquid mixture, okay, yeah, at 40 degrees Celsius. So the bubble point is the temperature at which liquid starts to vaporize. And given the partial pressure, okay, Pi of a species in the vapor phase is Yi multiplied by P, or xi multiplied by the vapor pressure. The total pressure will be the summation of the partial pressure of each species. So we have species butane and pentane over here. So the total pressure is the summation of these. Now, since we have the fraction of butane and pentane in liquid phase, we shall use this equation over here. So xi is the mole fraction in liquid phase and the vapor pressure in which we have found using the Antoine equation. So the total pressure is the summation of your mole fraction of each species multiplied by the vapor pressure of each species at 40 degrees Celsius, and sum it up, which gives you 2752 mmHg for your total condenser.